The wrapping function. To expand our trig definitions one more time, I need a function that takes in a number and sends out a set of coordinates. So how does this wrapping function work? Well, the wrapping function goes to the unit circle. The unit circle is a circle on the xy plane. It has a center at 0, 0, and it has a radius of 1. So this distance here is 1. This is called the unit circle. And the wrapping function goes to the unit circle and starts at this point. Now I know the coordinates of this point. If the radius is 1, this must be the point 1, 0. So the wrapping function starts at 1, 0, and then it treats x, the input, as a directed distance. If the x is a positive number, the wrapping function starts walking counterclockwise. If the x is a negative number, the wrapping function starts walking clockwise. The wrapping function is going to start walking along the edge of the circle until it has traveled a directed distance of x units. So once it's traveled x units, it stops, and the coordinates of the point where it stops are the coordinates that the wrapping function sends out. So again, x goes in, this distance is traveled, a comma b comes out. You say that's nice, but how in the world would we ever find the coordinates of that point? Well, here's the key. This distance x is an arc length along this circle, and we have learned that there is a connection between the arc length and the central angle of the circle, which I'll call theta. We know there's a connection between x and theta. In particular, we have learned this formula that the arc length is equal to the radius of the circle times the central angle, as long as the central angle is measured in radians. Well, in our picture, the arc length is called x, the radius of the unit circle is 1, and our central angle is theta. When you simplify here, what you learn is that the x, the distance, is equal to the theta, the central angle, as long as theta is measured in radians. Well, this is an amazing fact, and here's our big result. On the unit circle, walking x units is the same as rotating x radians. X and theta are the same number. This is a huge result. Seriously, this is a huge result because we've just found a way to link regular numbers with angles. Well, let's try it out. Suppose we take the number pi over 2, it's just a number, and I put it into the wrapping function. What's the wrapping function going to send me out? Well, I know the wrapping function goes to the unit circle, starts at the point 1, 0. Pi over 2 is a positive number, so the wrapping function is going to walk in a counterclockwise direction until it's traveled a distance of pi over 2. You say, I don't know how to travel a distance of pi over 2. It doesn't matter because walking pi over 2 units is the same as rotating pi over 2 radians. And I know that, that's just 90 degrees. So I must be walking to this spot. This distance must be pi over 2, just like this angle is pi over 2. On the unit circle, the central angle and the arc length are the same. Well, the great thing is I know the coordinates of this final point. It's up at the top of the circle. Remember, the radius of the circle is 1. So this distance is 1. This would be the point 0, 1. That's what the wrapping function sends out, 0, 1. How about the number pi over 4? What's the wrapping function going to do with that number? Again, it will start at the point 1, 0. It's going to walk a distance of pi over 4. I don't really have to think about that much. I can just rotate pi over 4 radians, which I know to be 45 degrees. So I know then that this is a distance of pi over 4, just like this is an angle of pi over 4. The wrapping function will send me back the coordinates of this point. Now this one seems a little trickier. I didn't land on a nice axis spot, so How in the world will I get those coordinates? Well, I can picture the coordinates that I need by dropping this perpendicular. What I really need here is I need to know this length, and I need to know this length. But haven't we seen this triangle before? This is a 45, 45, 90 triangle. And maybe you're thinking, oh, we should just label the sides 1, 1, and square root of 2. Well, not quite, because on the unit circle, the radius is 1. That means this length, here's a radius length right here from the center to the edge. That length is 1. To fill in the other lengths, I'm going to have to rely on the generic 45, 45, 90 triangle. What we know about this triangle is that these two legs are the same, and the hypotenuse is always square root of 2 times as much as one of the legs. We usually use the easiest version of this, 1, 1, and square root of 2. That's not going to work here, because here the hypotenuse, the x root 2 side, is equal to 1. I can quickly, though, solve this for x by dividing each side by square root of 2. And now I know that x is equal to 1 over the square root of 2. If I rationalize the denominator, I end up with x equals square root 2 over 2. So that means this side has length square root of 2 over 2, and this side has length square root of 2 over 2. Which means that the coordinates of this point are root 2 over 2, comma, root 2 over 2. Well, that's what the wrapping function sends out. Final answer, ordered pair, root 2 over 2, comma, root 2 over 2. Again, the significant part here is that we found a way to link regular numbers with angles in radian measure. Thanks for watching.